So for tutorial 8, question 1, a stream of air at 30 degrees Celsius and 10% relative humidity is humidified in an adiabatic spray tower operating at the pressure of 1 atm. The emerging air is to have a relative humidity of 40%. A. Determine the absolute humidity and the adiabatic saturation temperature of the entering air here. And B. Use the psychrometric chart to calculate part 1, the rate at which water must be added here to humidify 1000 kilo per hour of entering air, and 2, the temperature of the exiting air here. So for A, now in this case here we assume that the heat required to raise the temperature of the liquid in the spray tower is negligible compared with the heat of vaporization of the water, so that the air follows an adiabatic saturation curve over here, which is the constant wet bulb temperature line on the psychrometric chart. So we were given that the air enters at 30 degrees Celsius and 10% relative humidity. So we draw a line at 30 degrees Celsius over here and 10% relative humidity. So notice this curve line here. So this is 10%, 20%. Now if you don't know whether if this line represents relative humidity or whatsoever, you can check the writings on here. So this one is the relative humidity line. This is the enthalpy deviation line. Okay, so this is the dry bulb temperature. And from there, we want to figure out what is the absolute humidity. So we basically draw a horizontal line over. Absolute humidity means the moisture content. So this is about 0.0026 kilo of H2O per kilo of dry air. And the adiabatic saturation temperature. So we draw a line across towards the wet bulb saturation temperature and draw a line down to identify its temperature, which is about 13.2 degrees Celsius. So for part B, we want to calculate the rate at which the water must be added and the temperature of the exiting air. So for part B here, now previously the properties of the air entering is fixed, so we keep this fixed. So the state of the outlet air must lie on the wet bulb temperature of 13.2 degrees Celsius. Then from the intersection with 40% relative humidity, so we look for 40% relative humidity, which is around this line. The absolute humidity and the temperature of the exit gas can be determined. Okay, so the absolute humidity, again draw a line over like that. So this is our absolute humidity, which is about 0.0063, and the temperature of the exiting air is about 21.2 degrees Celsius. Now subsequently, the inlet and the outlet flow rate of dry air, okay, can be determined as so. So we were given that the inlet of the air is 1000 kilo per hour, and we multiply it with 1 kg of dry air divided by 1 kg plus its relative humidity of the water. So this is your total mass of the air, and then we get the mass flow rate of the dry air, of the air. Now the amount of water that must be evaporated, H2O, can be calculated as the difference between the outlet and the inlet water flow rates in the airstream. So MH2O is equal to 997.4 kilo of dry air per hour multiplied by the difference in its inlet and outlet water flow rates here, which is 0.0063 minus 0.0026, the inlet. Okay, and that gives you 3.7 kilos of H2O per hour.